Hello, there's Chris. There's Cheska. Wait a minute. Oh, there's another county heard from. Okay, don't try to do that to my head. Okay, good to see you. There's Maria. There's Kate. Whoa. Okay, I get it. Sort of. Wait, is this right before? Oh, I'm not even gonna ask. Okay, have a good lab, folks. Whatever. There's Michelle F. There's Yavi B. All that you can be. There's Cheska, who I almost thought I had a haircut but didn't, and who's offering treats. Wait, is that? Oh my God, is that Peaches? Wait, oh, Peaches, 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 Peaches. Okay, she's on mute, but who doesn't love the Peaches song? Oh my God, Princess Peach in the flesh. Wait, that's gross. In the anime. I mean, okay, whatever. That's awesome. I mean, who doesn't love Princess Peach, really? Bubble tea. Oh, bubble tea. Oh my God. Oh, her back. Okay. All right, I'm gonna say hello, guys. You were so good at getting me off. It's a good thing I love physics so much because I would never talk about it otherwise in this class. Hi, Shy. Good day, Michelle Q. Good at Michelle Q. Does she literally change every single time? I think Michelle Q is she's been like mysteriously all right, anyway, whatever. Good afternoon, Paulina. Good afternoon, Allison. Good after wait, someone else is here. Closed caption is here. Um, Okay, sorry. Good afternoon. I went to a wedding where Professor Walters dressed as Luigi and Professor Walters, female, dressed as Princess Peach. True story. No, not true. She dressed as don't tell me. Oh my God, what's the other one? What's the one she gets she deserves so much more press than she gets. Don't tell me. The other, oh my God. I'm so ashamed of myself. Don't tell me. I'll think of the other character, not the other. All right. Anyway, good afternoon, Jada. But she dressed as her. Good afternoon, Stephanie. Good afternoon, Yavi. Good afternoon, Freddie. Good afternoon, Brooke. Good afternoon, Michelle F. Look at Cheska. Okay, we covered Cheska's bag. Yes, we need to cover Cheska's bag. Just kidding. She drew them. Wait. Oh, you draw them? All right, that is the discussion for. Oh my God! Wait. All right, Q. You need to talk to me at some other. We need your art for the physics TCG, which you'll see the poster at the thing, and then you'll see the cards we have so far. But the person who does our art now is graduating. We need you for physics TCG. You need, what do you call it? Oh my God, I can't even think anymore. You need FOS 402, right? Like, let's talk. All right, anyway, whatever. But I'm not actually kidding. Milk tea was, don't do bubble tea. I'm the wrong era for bubble tea. I'm the right era for. Oh, I just thought of her name and I just forgot it. Okay, see, I don't even need you guys to get me off the topic. I just need my own psychological diagnosis. Yeah, a wedding. Yes, the wedding of, am I giving away too much when I say at Dr. Roberts' wedding, your instrumental professor? We all went to Dr. Roberts' wedding a long time ago and it was cosplay. I'm just saying, okay, I'm going to say that. I don't think it was one of the coolest weddings ever. Literally, his wife, whom we all know, his wife is named Leia. She dressed up. This is at her wedding. She was dressed up as Prince, and they are big, fans. She dressed up as Princess Leia. Her father walked her down the aisle dressed as Darth Vader and to the Empire theme. No joke. Now, Dr. Roberts was dressed as not something obvious. He was dressed as Doctor Who because that's a more formal costume wear, and like that worked as well. But anyway, it was a cosplay wedding, and the Walters is dressed up as. Why can I not think of her name? But the other female from, or the other unambiguous, whatever. All right, I draw that. Okay. Biggest plot. No, that's totally true. What I just said, it's completely irrelevant, but it is completely true. My whole family was there. My kids were dressed. Anyway, okay. One thing I'm going to drop the bad bomb while we're all having a good time. There it is in the chat. I'm just going to move on to physics now. Rosalina, that's who Rosalina, thank you. Like the Bruce Springsteen song. Yes, she dressed up as Rosalina. He dressed up as Luigi. Okay. And I've only seen, by the way, as a physicist, I've only seen 3 movies in the theater in like the last 10 years. Obviously, one of them was, Oppenheimer. I mean, I sort of had to see that, right? And one of them, of course, was Barbie. I didn't see them on the same day. I thought Barbie was better. And one of them was the Mario movie. Like, what else am I supposed to see in the theater in the last 10 years? And I thought the Mario movie was amazing. Okay. All right, just saying. Yes. Oh, Ken. Oh my God, the Ken song is brilliant. All right, Annie, we're gonna do physics. We got to do. I'm sorry about the exams. You see in the chat. I'm gonna move on because there's people hate it when I over apologize about this. You will get them. I totally, and I know last year you didn't even get, last semester you didn't even get them in time for your final. That was horrible on my part, and it does happen, and I have no excuse. But at least that I'm not going to do this. I know you need the feedback before you take a final. I totally, really. So I know this is already taking too long. There are reasons, but they're not good. There are excuses, but they're not good reasons, or vice versa. But you will get them, and I do understand that if nothing else, besides the fact that you want your grades, I know you need to see them before you. So there's nothing more I could say about that right now. I honestly do apologize, but we're just going to go on with physics. And I'm being very generous. And if you're just continuing to try to do the homework and you're handing in even remotely when you're supposed to, I hope you see that you are getting lots of points for that. And again, any homework you've ever gotten back, since we're getting to that part of the year where people are concerned about grades and stuff, just remember the weird policy I have. Like when you turn on homework in on time, like you get tons of points just for doing that. And then the rest of the point, and then you sometimes don't even get feedback right then. And I know, and that's an issue, but remember the deal is like you either get the feedback later or you get the rest, and then you improve it to get the rest of the points. Or you get the rest. If you never get feedback, you get the rest of the points, if that makes any sense. Okay, so you're still and you're seeing that hopefully on your side coming in more and more. I know we're getting to that time of year, but okay. Where I should talk more about Mario and less about physics. No, just kidding. All right. So what I'm going to talk about now, though. Wait, I'm assuming you can hear me. Wait, because I can't hear you. Yeah, okay. Thank you. Okay. So what I'm going to do now is start blasting through the last topic. I'm going to start talking about the homework that was just assigned that many of you actually turn in for Wednesday, which is great. The homework starts sort of reasonable and sort of pluggy chuggy, and then it gets very hard at the end. I know that. With all of the things, you'll still have time to redo it if you want or get all the rest of the points. But just know that by the end, what it gets to is a problem that often is one of the choices on the final exam. And that's what we will get to that in the lecture. But let's do the build up first. So I'm talking about, I'll screen share quickly, just so you know. I'm talking about what I'm about to go over is this. Wait, just so you can see, because I know some of you have done it, some of you not. This is the homework. This is the thing I'm about to go over right here. And hopefully this will be helpful to people who have thought about it and who now have questions that need answering. But even if you haven't started it yet, hopefully this will still help you. You should pay attention either way. Last quick question before I get rolling on this homework. Could you put in the chat, could you remind me where you are in lab? I believe you've started a circuit lab in lab, but confirm for me in the chat, what lab you just did or what report is now due. Okay, I'm looking at chat. I'm looking at circuit. Okay, that's what I mean. Well, I don't know what I just said, but that's what I mean. Yes, great. Okay, so quick thing too, I think I've mentioned this before. What I'm going to start dealing with now in lecture is the electrostatic force and the electrostatic field. Now, you can imagine that is ultimately quite related to the electricity stuff that you're doing in the lab. As always, you start playing around in the lab first, and then the concepts start maybe to get more clarified in the lecture. It's always confusing in the lab first. We know this. But just to emphasize that more in this particular arena, you're dealing with electrical circuits in lab. That is what's happening when charges are already in motion through wires around closed loops. What I first need to teach you in lecture right now, before it's explicitly, clearly connected, is I want to talk today about why the electrons are moving in the first place. Okay, so first we're dealing with the electrostatic field and force in lecture, and then you'll see how that ties to electrical potential and electrical current and electrical resistance as you're doing in the lab. The reason you jump straight to circuits in the lab is the same reason that's what happened in history, which is that circuits can actually be played with, observed, and measured in a lab in a way with far greater reproducibility and access than the somewhat abstract electrical force or electrical field can be. Okay, so I'm going to be talking about electrostatic force and field here in lecture. That gets charges in motion, and then then once they're in motion, it's called circuits, and that's what you can actually play with or measure in the lab. So I don't know if that helps at all, but that's the context. Okay. So what this sheet, I'm going to go back to the other screen in a second, but obviously stop me with any questions or concerns. What this sheet is trying to say first on the front page, it's trying to either remind you or present to you for the first time this universal force called gravity. And it's trying to say that there's this universal force called gravity that we have somewhat experience with, and that the universal force of electrostatics has exactly the same mathematical form. Okay. So the point is, we start with gravity because we feel like we can sort of picture gravity, many of us, or more specifically, gravity governs over masses. And we feel like many of us can picture, or we can picture and relate to macroscopic pieces of mass. And however masses pull on each other through empty space, it turns out microscopic protons and electrons pull and push on each other in the exact same mathematical way. So when in doubt, whenever you're trying to think of electricity, if you can bring it back in your mind to gravity, that's the idea. That's the helpful analogy. So I'm going to switch. So that's okay. So I'm going to switch boards back to, or I'm going to try. Hello. Wait. Okay. So back to the board. Yes. Okay. So first to remind you about how gravity works, and specifically to set it up by using that thing called a unit vector that we established back in homework 2. Here's the given. Okay. So I'll talk about gravity first. Okay. Briefly. First of all, the premise of gravity, the given, we're supposed to picture 2 point masses. So 2 dots of mass, like 2 amounts of kilograms, right? Somewhere in space. Now we're supposed to be picturing 2 arbitrary point masses. So first of all, they're point masses, i.e. they're particles, i.e. they are magnitudes of mass that we assume to be, or that we picture in our mind to be, occupying like an infinitesimal volume of space, right? That's what it means to picture a point mass, some amount of mass that is taking up essentially no space. Okay, so you got a point mass, right? That's a particle, like an infinitesimal particle. You've got, which by the way, is what in principle we were always picturing in physics 203 when we were ever talking about anything. We're, for what it's worth, like even when we say car in physics 1, we're really picturing a bit of mass at the center of that car and tracking that bit of mass as it drives down the road or whatever. When I say that, what I mean is when we say car, we mean in our mind a shrunken down, idealized version of a car, because what we're not acknowledging, we're not picturing a whole body of a car, because we're not acknowledging, or in these kind of problems that we're doing, we're not investigating or measuring or allowing for any motion of one piece of the car relative to another piece, right? The car is like a unit. So we just track. So it all moves as one. So we track the center of the car and we call that a point mass. Okay. So this is like not a new thing, but so if you have two point masses in the universe and they're arbitrary point masses, so there's no reason to assume that they're the same size. They're different sizes. When I say size, I mean mass wise, right? So maybe you have like a 50 kilogram dot over here, and you have like a 2 kilogram dot over here, right? That's like the assumption that we're picturing in our mind. Some really dense dot over here and some not so dense dot of mass over there. They each have, okay, and they're separated in space by some arbitrary amount and by some arbitrary direction, right? That's the original assumption. We're picturing two dots of mass separated somehow in space. So we're going to label the bigger of the two masses capital M sub 1, and we're going to label the smaller of the two masses like lowercase m sub 2, right? And again, this is all we're trying to be arbitrary here. So just whichever one is bigger, we just call it the bigger one. I mean, you get what I'm saying. And then, now here's where it gets a little bit, then we say, okay, now they're separated not only by a distance, by some distance, but they're separated in some direction. If you wanted to get from one mass to the other, you'd have to walk a certain number of miles in a particular direction. So that is a displacement, not just a distance, right? It's a vector quantity that separates the two masses. So we call that vector, that displacement vector, R with an arrow over it, making explicit that it's truly a vector. And to keep things straight in our head as a convention so that we're all on the same page, we say from here on in R, when we talk about direction, we mean the direction you'd have to walk in if you were going to go from the big one to the small one. It's just a convention. It could have been the other way, but we all want to be on the same page. So from here on in, whenever I talk about the R vector, the displacement vector, which becomes pretty important in E&M, in electricity and magnetism, the R vector is always assumed to point from the big thing to the small thing, okay? So that's the setup. Given this setup, so just two arbitrary things separated by an arbitrary amount and direction of space, the claim by Newton, the law of universal gravitation, or the universal law of gravitation, so according to, one mass will automatically exert a force on the other mass automatically, and a force is a vector. So one mass will automatically exert a force on the other mass with a force vector whose magnitude is given by the product of these three letters in the parentheses divided by the square of the letter in the denominator of the parentheses. Like the force will be a vector whose magnitude is everything in the parentheses and whose direction is given by r hat negated, the negative of r hat. Now that's a mouthful. What am I saying? And again, I'm talking about gravity right now. I'm saying okay, I'm saying force is a vector, right? Force is a push or a pull of a certain strength measured in newtons in a particular direction. If you want to know how hard mass 1 pulls on mass 2, or how hard, like the center of the sun pulls on the center of the earth, or whatever, according to Newton, the answer is given by this equation. And this equation denotes a vector. a quantity with magnitude and direction. Now, the magnitude is produced by everything that's in those parentheses, the magnitude. That is, you take the mass of one, you multiply by the mass of the other, you divide by the square of the distance between them. So the magnitude, the strength of the force is bigger if either object is heavier, and it's smaller if if the objects are far away from each other, right? But then there's also this other letter in there. Let me just get that out of the way right now. Actually, I'm going to go to the next. Well, I'm going to go to the next page. No. Now that capital G is not lowercase g. That capital G is not 9.8. That capital G is a universal constant in other words, no matter what the gravitational situation is, whether it's here on Earth, whether it's out in the Andromeda galaxy, whatever, to get the magnitude of the force between two objects, you multiply the mass of one by the mass of the other, and then you multiply that entire thing by this number. It's always the same number, 6.67 times 10 to the negative 11th newtons meters squared divided by kilograms squared. You don't have to memorize that number. You have to just be aware that it's always the same number. You have to be aware that the exponent for the number is tiny. It's 10 to the negative 11th. I mean, the exponent is tiny. So the number itself, the magnitude, is tiny. And notice the units look really like intimidating at first or obscure at first. The units of the universal gravitational constant are newtons times meters squared divided by kilograms squared. It sounds like a mouthful until you realize that, in fact, those units not only are make sense, but in fact are the whole reason for the number. If you think of the units, if you look at GMM over R squared, you see R squared is in the denominator. So there's meters squared in the denominator, and then there's mass times mass in the numerator. You're multiplying kilograms by kilograms in the numerator. So what the units of this number do is they cancel out the meters in the denominator, and they cancel out the kilograms from the numerator, and then they multiply by newtons. But this crazy number is doing basically, it's just ensuring, it's a proportionality constant that just ensures that after you've multiplied all the relevant quantities together, or after Mother Nature has multiplied all the relevant quantities together, including these units, then what you end up with is a quantity measured strictly in newtons, as it should be, because it's a force. So in other words, we wouldn't even need, one of the reasons you don't have to memorize this number, even though you should be aware of it and know it's always the same. You could always look it up because it's always the same number. We wouldn't even need the number if we were willing to measure things in like centimeters, grams, and milliseconds or something. It's just there to scale everything appropriately to meters, kilograms, and seconds. Okay, so you multiply all these numbers in the parentheses to get a magnitude. But what about this R hat? What's the deal with that? Well, that's telling you the direction of the force. How so? Remember from homework 2, I'm going to review now quickly, but recall from homework 2, when I write R hat, what I mean always, when I write any vector with a hat over it, I mean the vector itself divided by its own magnitude. I'm going to go to the next page now. Okay. I'm also in this. Wait, great. Great question. Great question. Hold on. The whole equation, so the question, there's a question in direct chat, which is great, which the question says, is this a triple equal sign equation or is it a double equal sign equation? I love that question always in general. If you're talking about the gravity equation, I mean, so technically, I mean, that's a close call. It is let me put it this way. Technically speaking, it's a double, and I'll tell you why. Technically speaking, it's a double equal sign because it's a discovery. because this isn't actually because we knew what we meant by gravity way before Newton figured out that this math works to predict gravity. Like what gravity is the force that any one object exerts on any, what gravity is the pull that any one point of mass exerts on any other point of mass. Like, and we've been observing gravity and gravity dictating orbits, astronomical phenomena for like centuries, millennia really, before Newton came along. So we had this concept. Well, I'm getting ahead of myself. There's a concept of gravity, which means how one object pulls another object in space. Newton figured out that the mathematics of it, that the exact details of it are this. And that's partly putting together, that's a discovery. That's putting together a lot of data from Kepler and Copernicus and things like that, and then making a big leap and conjecturing that the details of gravity work this way. It's not the definition of gravity, and we knew about gravity before we knew this, so it's not necessarily, no one's necessarily saying that the minute you say the word gravity, it has to mean this, but it does turn out to be this. So strictly speaking, it is a double equal sign. The reason I'm dwelling so long on this question, though, first of all, I just love it when anybody cares about that. But second of all, say you're asking it for like exam purposes or something, like if part of what you're asking when you ask is it like, this is a law, this is definitely a fundamental, one of the most fundamental laws in physics. So it certainly counts as a GDP, as like a step 3 in any kind of problem solving method that you do on any kind of exam or homework or whatever. Put another way, this law, I'm saying to everybody, not just who asked the question, this law, certainly I would never ask you to prove or derive. Like I can't ask you to do that. I'm not telling you the proof of the derivation. It's not even it isn't a strict proof. This is like a big, big discovery. So to move on in a moment, but like you can treat this thing like an axiom or a law or a fundamental principle, a general definition or a principle, but it really is a principle, not a definition. So it's a double equal sign, but it is definitely a step 3 in any problem solving method. Does that, oh, okay. Okay, cool. All right, great. But great question. Okay, right. So to everybody else who tuned out like 45 minutes ago, not surprising, you don't ever have to, you can use this as a starting point on any relevant exam problem. Okay, but now the R hat, the R with the caret at the end of it is a tricky little bit of notation that we've seen once before. We sort of put some effort into establishing once before, but it could be, what is it doing there? What does it mean? It certainly intimidated me for a long time because it's just important enough to be included. And just important enough to make actually a big difference in the long run in physics, but it's not ever clear to anybody what they're supposed to do with it. Here's why. Here's what it is. I'm just writing the equation again just so you have it here. Okay, so here's the equation. So here's the equation, right? By R hat, we mean this. Okay. Okay. Here's the deal with R hat. R hat in English, R hat is the unit vector for R. The way for any vector at all, if you have any vector, vector A with an arrow over it, if you take the vector A and you divide by its own magnitude, you get what we call A hat, or the unit vector for A. In other words, if you have a vector, like the vector quantity, like 3 miles long, pointing to the northeast, if you take that vector 3 miles far and pointing to the northeast, you take that vector and you divide it by its length, 3, which is exactly what I'm saying here. You take a vector and you divide it by its own length. So if you take 3 miles to the northeast and you divide by 3, what you get is a vector which points to the northeast, but has a magnitude of 1 mile, right? Like that's the whole idea, is a unit vector is you take a vector, divide out its own length. So then you end up with a vector that points in the same direction as the original vector, but only has a magnitude, a size of 1 unit on purpose every time. So it's a piece of notation. So what's the purpose of this? Or like, why would we do this? Because then it allows us to focus on the pure direction by itself without getting distracted by magnitude, just like we already have a way of focusing on the pure magnitude without getting distracted by direction. In other words, if you design this thing called a unit vector, r hat, then from now on in our minds, we can always think of any vector. Any vector is a simple product, can be thought of as a simple product of a pure length multiplied by a pure direction, right? Or put in, right, like a vector now is like the number 3. So that original vector, 3 miles at pointing to the northeast, you can think of it as 3 times 1 pointing to the northeast. It like separates the two pieces of a vector in our minds mathematically. More specifically, it allows you to think of the vector as something that was constructed. Like with R, okay, like you can go backwards in your mind and you could think, okay, so in this picture right here, like R is some the blue, the black, the charcoal colored arrow is r hat, some arbitrary displacement vector just pointing off into space. But if we construct the unit vector for it, the brown vector r hat, then r hat is a vector that is indicating the direction of the original r, but is literally only has 1 unit of length. So in our minds, what we can think of r, the vector, as having been constructed in the following manner. We can think like, okay, someone walked along and made r hat. They made a vector that pointed in a certain direction, but only had a length of 1. And then we scaled up that vector or scaled down, like we stretched it or we shrunk it by the length r. So we ended up getting this whole vector r hat, r arrow. So from now on, we can think of vectors as being constructed from first you construct a unit vector and then you scale it by a certain amount. This allows us to picture something like gravity. So here's gravity now. The idea behind gravity is, like, so here's the law of gravity. The idea is we have M1 over here and we have M2 over here. And before we do anything else, we just construct a unit vector, r hat, that points from M1 to M2. So we make this little arrow that points from the big thing to the small thing, but only has a length of 1. So we have that unit vector, and that's this right here, right? Then we go ahead in a separate part of our brain and we multiply the mass of one times the mass of the other. We divide by the distance between them squared, like we divide by just r, the letter r, which is just the magnitude, right? We divide by the distance squared. That whole number together, we treat as one big number, and we scale up or scale down the r hat vector. So we had this r hat vector that was just a unit 1 pointing from mass 1 to mass 2. And then we scale it by gm m1 times m2 all over r squared. And by doing that, now now we have a new vector that has the same direction as R, but has a totally different size and is measured in newtons, right? So this is now a force vector, right? But last thing before you draw that, then there's this negative sign here that says, okay, now take that whole vector and flip it into the opposite direction. So we started by saying we're pointing from M1 to M2. Then we scaled it up, or really probably scaled it down by the tiny number, 6.67 times 10 to the negative 11. Blah, blah, blah. And then it's saying now flip the whole thing. So we'll end up at the end of the day, we'll end up with a big force vector, right? That was built from the displacement vector. So we're saying the gravity is a force that is constructed from displacement. You take a displacement vector, you scale it up or you scale it down by a bunch of mass and distance parameters, then you flip that vector, and now you have a force vector that is the final answer. That is the force of gravity, like measured in newtons. And why do we flip it? Because at the end of the day, according to the law of gravity, it is always the case that if you want to know the force that M1 exerts on M2, then the force that M1 exerts on M2 points from M2 to M1, right? We start with this designator, this R that goes, okay, point from M1 to M2, but then we flip it because at the end of the day, we want to say the force that the sun exerts gravitationally on the earth is a force that points from the earth to the sun. Why am I saying that? Because it's a pull. The sun pulls the earth to the sun, right? So gravity is always a pull. That means that it always, so this negative sign at the end of the day is saying to us that it's a pull toward the source of the force. It's attraction. Always. That's what the negative sign ultimately means. If you follow. So I know it just said like a lot of weird, you might have done the homework and gotten it all right and not understood any of this. I understand that. Like none of this has to do with plugging in the numbers. I'm just telling you what the vector notation means. A, because it's intimidating, I think, but B, because it's actually important in the end. What we're saying is, and we're setting up a model for electricity. We're saying at the end of the day, you think of the universal gravitational force that one object exerts on another as a pull from one object of the other towards itself. And that direction of pull is captured by the negative sign and the unit vector, like always. Hold on. That's abstract, but and obviously we're going to do the examples, and well, we're going to carry it over. Well, wait, oh my gosh, I'm so glad Mohammed I was just about to pause and see if I was making any sense to anybody. What a great question Mohammed just asked. Okay, so let me pause for a second. So the answer is yes. So okay, let me totally pause for a second. So I've just been talking about math, or specifically unit vectors, for like 20 minutes. But yeah, what does this really mean in English? What we're really saying is, all right, so the answer to Muhammad is yes. I mean, he wrote, does the sun have a gravitational force too? And more specifically, what I'm really trying to argue here, or what this law says, is that every single point mass in the universe automatically exerts a gravitational force on any and every other point mass in the universe all the time. Like, that is a very important point, and it is not at all obvious. Like, I'm really glad Mohammed just asked that. Let me, and that's a thing we want to definitely take away from all this. Hold on. So I'm just writing it again. Okay. In English, what I'm saying is, okay, let me dwell on that for a second. I'm really glad Mohammed just asked that. What we're claiming, and this is a big deal, and we didn't know this before Newton. This is part of, and it is a discovery or it's kind of a leap of imagination, actually, but it turns out to be true. Like even Newton couldn't like prove this. He could just strongly defend it and start using it and start acting as though it was true. And the more we act as though it's true, the more it does seem to be true. I mean, in other words, the more predictions we make based on this, the more they come out to be accurate. What we are saying with this equation, so and why I'm being so abstractly mathematical, why I'm getting into all this, like imagine you have this arbitrary mass over here of an arbitrary size, and it's like an arbitrary displacement away from some other arbitrary mass. And by arbitrary, I mean randomly chosen. I mean like not special. So what we're saying in this equation is for any M1 that you have over here, any electron or the center of any atom or any molecule or like any planet, any object over here automatically pulls on any other and every other object that you think about over here. Like any bit of mass over one place is automatically all the time pulling on any and every other bit of mass at every other place in the whole universe. Like we believe this. That's why it's called universal gravitation. And we don't think it's obvious. We do think it's a big deal, but it's a very big deal. Again, I'm not saying this makes sense. We'll talk more about that at another point. And it certainly didn't make sense to anybody when it came out as a claim in the mid 18th century or the early 18th century. But it is what we believe, that every dot of mass everywhere in the universe automatically pulls on every other dot of mass. And we're saying it's not all the same pull. If it were all the same pull all the time, and if there were no other pulls or pushes in the universe, everything would just crash together. Like we're saying that there's other pulls like this in the universe and other pushes, even more important, in the universe called electricity, that balance this stuff out in many circumstances. And we're not saying that everything pulls on everything the same way. We're saying the bigger two things are, the more they pull on each other. That's the M's in the numerator. And we're saying the closer two things are, the more they pull on each other. That's the R in the denominator. But we are saying that every bit of mass automatically pulls on every other mass. And that is a huge deal. And I keep saying automatically here. What do I mean automatically? Hold And this gets into also the direct type, like why I couldn't ask you to prove this on an exam because like that'd be very unfair to say the least. Like this kind of force, this gravitational interaction is known as fundamental. It seems to be part of the glue of the universe. It seems to be just the way things are in the universe. It's not the result of other things. Other things are the result of it. And like why the universe is this way is certainly a very important question and has been for like I'm not saying like well duh, of course the universe would work this way. No, but apparently it does. So let me be clear, and then I'm seeing the chat. Wait. Well, okay. So isn't that just the assumption when you say automatic? I'll tell you what I mean by automatically. Hold on, off. Um, okay. So, no, I think this is a great question. Now, there's two parts to what Mohammed just put in the chat. He said, isn't that just the assumption when I say automatically? So I definitely want to address in detail what I mean by automatically. But as far as assumption, let's be careful for a second. Like originally when Newton came up with this, maybe one could say it was a conjecture. Like arguably, there wasn't a strict mathematical proof or even a strict chemical or something proof that supported this originally. I mean, it came from a lot of really, really good reasons. And specifically, it is what this is originally, this law is a synthesis of tons of astronomical data, like orbits of planets and asteroids and comets and things like that, that had been collected for centuries, and particularly a similar what's the word, compiled by Kepler. Like, so what this law in its starkest form, this law is sort of like the conclusion of all of this data about outer space that was very, very, very precise data and had been accumulated over a huge amount of time and put together largely by Kepler. So it came from somewhere, this law, okay? But then more to the point, the reason we believe it today, 3 centuries later, is because we keep testing it and we keep making predictions based on it that come out true. Predictions such as when is one thing going to eclipse another in the sky, right? Like the reason we know when eclipses are, like not just of our sun or moon, but eclipses of planets or Jupiter's moons or whatever. We know all of these things to such a high degree of precision because this math predicts those events. Number one. Number two, and I'm loving this question. I'm totally not making fun of this question, but number two, one other like big prediction that was made with this law as you all know, in like 1969, which is after the work of Einstein, but not based on the work of Einstein. In 1969, we launched a rocket that landed on the moon and people got out of it and walked on the moon. And by the way, I do believe that. It did. I believe that. Okay. I mean, I believe our government is capable of corruption. I believe our government is capable of conspiracies and of lying to us. Of course, I believe our government is capable of lying to us, but I'll tell you this, for those of you who are concerned about conspiracy theories or thinking that the moon landing was faked or something like that, look, I'm not saying that the government isn't ethically above that, but I'm saying this, in 1969, I promise you that missile technology, trajectory, projectile, ballistic technology, i.e. like our military technology was far more advanced than Photoshop technology. Like, you know this, like we were in a Cold War. We were worried about other countries. We were developing missiles and had been since World War II, right? We didn't have freaking Macintosh computers in 1969, but we did have rocket launchers. So what I'm just on a total weird rant sidebar, I'm just saying the technology required to fake a moon landing is far more advanced than the technology required to actually do one. Okay. I literally don't even know how they could have faked it. We literally didn't even have like, you know what I'm saying, okay? I mean, and if you don't believe me, fine, like whatever. I mean, it's not on the exam. We can all believe whatever we want. But I'm saying this, if you do have any interest in like believing that we've been to the moon, which is sort of amazing, 250,000 miles away, I can tell you this, it was based on this equation, okay? Like one of the tests of this equation is that like rockets work and orbits are predicted. So I'm just saying all that to say this is a very powerful equation that like matters to physics and to NASA, like even into the 20th century, where we have developments from such people as Einstein that, you know, we all regard as modern heroes. They didn't change this equation, or they didn't change our use of it to get from one point to another in outer space. So that's all just to say it's not, and with all due respect to the question, it's not an assumption. It's a highly, highly tested claim. It's very tested because it was so controversial when it first came out. But now, what do I mean by automatic? I mean, this is a part where Mohammed's very, very right to ask and push about this. Like, what do I mean when I say automatic? What I mean is that unlike other forces, I'm watching the clock, by the way, and I will everything I'm saying right now, why I'm getting so like excited is if any of the concepts I'm saying are meaning anything to anybody or doing anything, they all carry over to electricity. They're just like harder to picture with electricity, and they're hard enough to picture with masses. So everything I'm saying about fundamental, about action at a distance, about automatic R hat, all is everything I'm saying right now about how the sun pulls on the earth, or the earth pulls on the moon, or the earth pulls on a brick that's falling from the sky, or Jupiter pulls on one of Jupiter's moons. I'm saying all of these things pull on each other automatically with this force known as gravity. And it turns out to be automatic in the same way that protons pull on electrons, or electrons pull on protons, or protons push on other protons. What do I mean by automatic? I mean this. I mean, first of all, that no material contact is necessary. This is one of the mysterious, controversial, crazy things about gravity and electricity, that for the sun to pull on the earth, the sun doesn't have to touch the earth. That's a big point. Like for me, for my hand to exert friction on my other hand, I have to rub my hands together. For me to exert tension on a fish through a fish line and pull the fish out of water, I have to attach a string to the fish, right? Or, or for me to support the cup of coffee on my desk, the desk exerts an upward normal force on the cup of coffee. The desk surface touches the bottom surface of the coffee cup. Those are all contact forces. What we're saying about gravity and ultimately about electricity is that gravity appears to be testably fundamental to the universe, in that when we say the sun pulls on the earth, or the earth pulls on the moon, or the earth pulls on a human being and the human being stands on the ground, doesn't go floating up into the sky, we're saying that that pull happens whether or not the two objects are touching each other. Now that's a big deal. I mean, that's why it's like good that Muhammad's pressing on it. Like, but that is what we're saying. We're saying the sun pulls on the earth just because the sun exists. This is what we mean by automatic or fundamental. If the sun exists and the earth exists, they pull on each other. It's a property or a consequence of having mass. If the sun has mass and the earth has mass, each one of them automatically exerts a pull on the other. If there's nothing between them, they exert this gravitational pull of, according to this math that I just wrote down. And by the way, if something is between them by chance, like if there's even if there's something between them, the gravity still transmits. Like if the moon gets in the way, like eclipse, if the moon gets in the way of the sun and the earth, the moon doesn't block the gravity. Gravity exists automatically, or the real term for this is gravity is a phenomenon known as action at a distance. It just happens over distances, whether or not there's anything intervening in the distance between the two objects. Again, I'm going to move on in a second, but I hope it's clear. I'm loving Muhammad's question and the private person who asked about the R hat. I'm loving Muhammad's question. If it sounds like I'm arguing with him, I am not. I am arguing with the word assumption, I guess. I am getting defensive about the word assumption, but I'm not arguing anything else. And I am applauding the fact, if he doesn't, I don't want to speak for him, but if Muhammad's saying, this makes me a little bit, I'm not sure how I feel about this force. Good, join the rest of humanity, certainly in the 17th and 18th century. And nobody should totally, I hope you understand the words I'm saying, but if you understand them enough, you would, if you're thinking and paying attention, you would go, okay, that's a little weird. Like, yeah, it is. It's so weird that we call it fundamental, which is really weird. It's not fundamental because it's obvious. It's fundamental because apparently it happens just if we exist. If a mass exists and another mass exists, they pull on each other regardless of what they're doing. They don't have to have velocity. They don't have to reach out and grab. They don't have to have any matter in between them. That's what we mean by fundamental. Maybe you could say in the chat whether that may not fully satisfy you. And it's not the last time I'm going to talk about this idea. But if it sort of made sense, maybe let me know in the chat. But now I'm going to go on because I know I'm going to say whatever all I just said about gravity. Turns out, same thing about protons and electrons, or protons and protons, or electrons and electrons. Turns out, So now I'm going to say, whatever you can picture about any dot. So, okay, bottom line to Mohammed's question, like, yes, I'm saying or gravity is saying, the idea of gravity is saying that everything in the universe, every bit of mass in the universe automatically pulls on any and every other bit of mass in the universe because apparently that's how the universe works. I mean, we could say more about it, but that parent, and it's very reasonable to say, why does that happen? But let me also say, it's also very reasonable to say, well, why is there mass in the first place in the universe? Why do things have mass? Why does mass exist? Or why is mass a thing? Very reasonable question. And you know what my answer is? I have no idea. And I don't mean that sarcastically. Like, great to wonder about some people who do a branch of physics known as string theory believe that maybe someday they actually have a blossoming answer to this question of, like, what is mass in the first place? But but we don't have it now. Like, mass is just where we start our understanding from. And therefore gravity. Now, similarly, there's a thing in the universe called charge. I don't know why. And I don't know why it comes in two forms, but apparently it does, or at least the way our human minds understand it, it comes in two forms, positive and negative charge. It's a fundamental property of some matter. Some matter doesn't, all matter is made of smaller matter. Some matter doesn't have any charge at all, apparently, like neutrons. But there are fundamental little bits of matter called protons and electrons that do carry charge, and always the same amount and always in discrete quantities, which is convenient. I don't know why. And again, I'm not being sarcastic. Like, these are the most terrific questions of all time. I just literally don't know. But I know this. If you have any two arbitrary points of charge, if you have a package of charge over here and a package of charge over here, and they're separated by a displacement r, they will automatically pull or push on each other in a manner. They will exert forces on each other in a manner that is dictated by math that is remarkably similar, identical, to the math that governs gravity. Gravity was discovered first, and then this electrostatic phenomenon was discovered later, and just discovered to work very much the same way. So this so this electrostatic thing. Okay, so if I ever use the word interaction, it means exactly the same thing as force. Force is interaction, interaction is force. It means one object pulling or pushing on another. So there's this thing called the electrostatic interaction given by Coulomb's law, which works like this. It says that one point charge will pull or push on the other point charge with a force vector whose direction is given by r hat, and then either plus or minus, depending on what kind of charges they are. So same thing. You first construct a unit vector that points from one to the other. Sorry. And then you scale up or scale down that unit vector by the product of the charge of one, the charge magnitude of the other, times the charge magnitude of the other, divided by the square of the distance between them. And then multiply the whole thing by a universal constant that does the same thing as the gravitational constant, but it's a different constant. Mass is measured in kilograms. Charge is measured in something called coulombs. So the constant in the equation has to cancel out the coulomb squared from the numerator and cancel out the meter squared from the denominator, and then multiply the whole thing by newtons to make the whole thing a force. Like it does the same thing as the other, but it has to cancel out coulombs instead of kilograms, and it scales it to a different level. So it turns out this constant, which is another K in our class, we had K meaning the K of Hooke's law, then we had a K written with serifs. That meant the K of angular wave number. Now we have yet another K that I try to distinguish from the other by putting a little subscript, a little electrical subscript on it to make it clear. This is called the Coulomb, the universal Coulomb constant, or the electrostatic constant. And what it is, approximately, the other one was a tiny, tiny number. This one is a huge number. 8.99 times 10 to the 9th, positive 9th, newtons times meters squared over coulomb squared instead of kilogram squared, okay? So this equation works the same way, You make the unit vector, then you scale it up or scale it down by the product of all those other numbers, and so now you have one big force vector. Just two catches to this. One, here, like, do you flip the unit vector like we did before? Notice here it says plus or minus. Well, here the deal is, some charges are positive and some are negative, right? Well, okay. Some are positive and some are negative. To put in perspective, and they all come packaged in protons and or electrons. Conveniently, a proton has the same amount of charge as an electron, only a proton has positive amount and the electron has negative, as you all know from chemistry. Now, it would be really convenient if the charge of a proton were 1 Coulomb. That would make our life really, but it's not the case, just because of the order in which things were discovered and it scaled back. Whoa, I just lost my hold. The charge of 1 proton is the same magnitude as the charge of an electron, but it is not a Coulomb. It's much smaller than that. Hold on, I'll just get my stylus. So it turns out that the charge of a proton, which we call lowercase e, is approximately positive 1.60 times 10 to the negative 19th coulombs. The charge of an electron is approximately negative 1.60 times 10 to the negative 19th coulombs. So it's inconvenient, but what we're saying is, when from here on in, if I say a coulomb of charge, right, I'm saying that one proton has like 16 times 10 to the, it has 1.60 times 10 to the negative 19th coulomb. So what is like 10 to the 12th is a trillion, 10 to the 15th is a quadrillion, 10 to the 18th is a quintillion. So if I ever ask you to picture a coulomb of charge, what I'm really asking you to picture is like 16 quintillion protons. I mean, protons are tiny, right? And electrons are tinier. If I say picture a coulomb where there's 1 coulomb of net positive charge over here, what I'm saying is picture like 16 quintillion protons jammed together, tightly packed into like a Euclidean dot, which actually is possible because protons are that small. It's certainly possible with electrons. So a point charge of 1 coulomb would be a huge number of protons packed into a tiny volume, or etc. That's for perspective. So, but notice, positive times a positive. Remember, a positive times a positive equals a positive. A negative times a negative equals a positive, and a positive times a positive, remember, equals negative. Why? And so does a negative times a positive. Why would I say that? Like, who cares? Well, because it works perfectly, because the whole point is, if you plug in charge values into the numerator of this equation, right, at the end of the day, if you get a negative sign, if it's like negative times a positive and you get a negative sign, then you're going to flip the vector like gravity. You're going to flip the vector and it'll be a pull. But if you multiply out the charges and you like do positive times a positive or a negative times a negative, and you get a positive number, then you'll leave the unit vector the way it is and you get a push. In other words, as you know from chemistry, like charges repel and opposite charges attract, right? And it works perfectly with the math. If you think about it for a second, positive times a negative or a negative times a positive makes a negative, and negative is pull. Negative is attraction. That's what we just established back with the gravity equation. But positive times positive or negative times negative makes a positive, which means leave the unit vector alone. So the amount of force that a proton exerts on an what a proton does to another proton is it exerts a force outward from the first proton to the second. It pushes it out. What a proton does to an electron is it makes a negative sign. It flips the unit vector and points back at it. So it pulls it in. I don't know if that made sense or not, but I'm saying we're using the same convention as with gravity, which is positive means push, negative means pull. And here sometimes it is a push and sometimes it is a pull. It depends on the types of charges. Okay, I know we only have 5 minutes. I know we have to start crunching some numbers here. Obviously, we're going to continue this on Wednesday. Right, and then you have wait. I'm assuming, someone tell me in the chat. I believe we have class Wednesday and then you're on break. Is that correct? I think I've lost everybody. I believe we have class this Wednesday and then you're on break next week. Is that crazy? Yeah. Yes, it's crazy. No. Okay. Yes, that's true. Okay. Thank you, Michelle Quach. Michelle Quach, you better. Okay. No. Great. Correct. Okay. Thank you, Paulina. Thank you, Maria. Okay. Great. 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 Okay. So okay. So with the 6 minutes, 22. Okay. 20. Right. So that's a week from today. Perfect. Okay. Thank you. Yes. Thank you. That's helpful. So I'm just going to do, so I'm going to blast. So the beginning of the sheet, so it's a weird concept. And it's a unit vector notation. Hopefully I've now explained how to understand the electricity equation. It's modeled after the gravitation equation. Hopefully now you have some concept. I don't expect you to believe these equations yet, by the way. If you're literally like, I get what he's saying, but I don't believe it, that's probably a good place to be. Because the more you understand what I'm saying, the more you have good reason not to believe me yet. Again, back to Muhammad. Like, if you think this is all like, well, I can do the math, but I don't like really feel like this is the way, then fine. I'm with you. But as far as the math, then the beginning of this sheet is kind of plug and chug. I'll do it quickly right now, and then we'll get to the harder part Wednesday. Like, if you get to the problem A1, like, so in the first example, I'm watching the clock. In the first example, we have, and sorry. And in these cases right now, in these first examples of A, 1, 2, 3, 4, 5, they're really asking you for the magnitudes of charge. Like, I'll talk about the directions more next. In other words, for A1, FE equals KQ1, Q2 over R squared. I'm just looking at the magnitudes now. I'm not looking at the directions. K is approximately 8.99 times 10 to the ninth. You can round that to 9 times 10 to the ninth Newton meters squared over Coulomb squared. Q1 in this case is +3. Q2 is I'm sorry. Q1 is 50, is +50. Q2 is -3, and it's all over 5 meters squared, right? These are coulombs. These are coulombs, and these are meters squared. So if you do that out on a calculator, you get, I believe, approximately 5.4 times 10 to the ninth newtons. Like, the meters squared cancel, the Coulomb squared cancel. So you'll get a force, I'll write on the next page. You get a force magnitude. If you just do the math, if you just plug into the equation, you get a force magnitude. I'm going to write it again. This is 50. This is 3. And R for this equaled 5. Right, so for this example, number 1, FE, the answer, the answer equaled 5.4 times 10 to the 9th newtons, and it pointed, this is how you, it pointed directly from the big mass to the small mass, which is connoted with this R hat. In other words, I'm putting a plus sign on this whole thing because both the charges were positive. So the whole answer is positive, and the whole answer points therefore from the 50 to the 30. So it means that the 50 is pushing away the 30 with a force of 5.4 billion newtons. That's what this is saying. Okay. And that's the answer to the first one. That's it. There's no more that you have to say, and there's no trick. Now, the next, I know we have like 2 minutes. I'll just summarize, and we'll pick up on this on Wednesday. The next 4 examples, all they ever do is change the receiving charge. They never change any other number except for the charge that's like receiving the force. And that's technically called what I just want to leave you with. I know it's just about 1:30. From here on in, I guess it does say on the sheet, like whatever the big charge is that's creating the force, or that we're looking at its force that's being created, we call that the source of the force, the source charge. And whatever's receiving, we call the test charge. The reason we call it the test is because, just like in this example, you can swap in and out, and you can test different effects of the original source. The source sits there at a certain distance, and we're trying out different recipients for that source. Now, note, Newton's third law is still true. We could just as easily flip our attention and look the other way. Like every single time the source is pushing on the test, it's also true that the test is pushing on the source with the exact same amount of force. We're just not looking at that, but it would be the same answer each time. We're going to pick up on the next 4 examples of this, or exercises from the sheet. Like maybe now that you understand, maybe try the homework if you haven't. We're going to pick up on Wednesday, but here's the thing I want to say. The point of this part of the sheet is, if you get what I just did in the first exercise, I just plugged in and multiplied and divided, you could just keep plugging in for all the next 4. You could just swap out the +3 for a -6, and then swap out a +5, and then a +1, then -2. You could just redo it every time. There's no surprise, there's no trick, and you'll get it right if you plug in every time the same equation. But what I'm trying to show you with these examples is that actually there might be an easier way to do it. So if you see a trick, a way to sort of cheat your way through, like without having to redo the equation every time, yes, that would be good. That's what you're looking for, is a technique to not have to redo every time. That technique is ultimately called looking at the field, whether you call it that or not. Anyway, so we'll pick up on this Wednesday. You've been very patient. I hope my answers to the questions were okay. Oh, there's something in the chat. Sorry. I didn't get it. No, it just, maybe I showered in the last month. I don't know. Okay. All right. Have a good, everything, everybody. And I'll see. Oh, that's very nice. Oh, so, wow. All right. I will see you, and I'll be in my office tomorrow for what it's worth. Blah, blah, blah. Facts. Okay. Have a great night.
Say bye, Avani.
Oh my God. Bye, guys. Have a great laugh.
Yeah, lab.
Laugh. Okay. Have a great laugh. You guys. Okay. Wait. Tell me when you find out. Okay. Yeah. And Shawnee, are you there, or are you good? You have a question? Should I go? Going once? Going twice?